All right, guys, we are having our exam on Monday, as you know. It'll be in the auditorium, as usual, normal business. I think it's 27 questions long, so similar to what you've had before. It is covering all circuits. So capacitor circuits that we had at the end of chapter 2, capacitors, I'll write this down in a minute, but capacitors, and then into chapter 3, current, power, and Ohm's law and resistance, current resistance, Ohm's law, and power. And then in chapter 4, we see resistors in series, parallel, combination circuits, and multi-loop circuits. In chapter 4, we will not cover RC circuits. We'll pick that up after this exam. Nor will we cover household circuits. So if you ever see a circuit that has both a resistor and a capacitor as you're practicing the old exams, we're not going to do that. Anytime you see RC circuit with both a resistor and a capacitor in the circuit. Now you'll see them separately, of course. Resistors in one thing and capacitors in another. But if you ever see an RC circuit, we're not doing that. And likewise, if you see stuff about your household stuff, the GFCI, circuit breaker, that kind of business, that won't be in there either. We'll pick that up. Okay? Y'all excited about the exam? Have any big plans for the weekend? Studying. Oh yeah, you have an exam. I finished writing the exam. I woke up at like midnight. When you call that this morning or yesterday? I'm not sure what you call that. Is that this morning? Yeah. I finished it up. And I thought I had class today at 2. I woke up, I don't know if y'all ever do this, but I woke up, and I'm team teaching this course with a bunch of other chemistry folks. And I thought that this was my day to teach it, but of course I hadn't prepared. And so I woke up at midnight and I was like, oh, do I have 406 today? I'm like, oh, no. And so I got up, but it turns out I don't have that class. So I got up for them. I got up for y'all to finish your exam.
Thank you.
Okay? We first have a few questions that we did not finish up on the concept test. So let's just do that. It'll take just a couple minutes. And then I'll go over the material for the exam, and if you have any questions, we can deal with it then. I'm going to be out this afternoon, unfortunately. We're going camping. So we're going to Tickfaw State Park. Who's asked us? Is he over there? Yeah, Tickfaw. It's one of our favorites. All right, we just have a few things, and you'll see some questions similar to this. I think we left off with this one. What is the branch, or what is the current in branch P? This is branch P right here. What is the current? I'll show you some other currents that are flowing. You will have questions like these on the exam for sure. This is an application of the junction rule. It says that incoming currents equal outgoing currents. What is the... Goodness, bless you. All right, I'm going to stop at 55. All right, awesome. So D is the right answer. Notice we have 8 amps going in here. 8 amps, and then I have 2 amps going out, so I have to have 6 amps coming out here. Our incoming current is 8. Our outgoing current also has to be 8. So I have 6 and 2 is 8, also 8. This isn't a joke, but it's just sort of a story. My wife and I, we were out walking downtown. It was kind of late, and this guy comes out of one of those bars down there, Roxas or whatever, I don't know. And he had obviously been, is it Roxas or Renee's? They had both of those. Anyway, this guy walks out, and he had been, he'd been drinking a lot. And he comes out and goes, "Grr," and lets out a big old belch right in front of my wife. And I said, dude, how dare you do that before my wife, before her? And he said, oh, I'm sorry, next time I'll let her go first. That didn't really happen. That was a joke. Okay, we're gonna skip this one. Those of you in the Wheatstone, this is like a Wheatstone bridge, but it's not that important. Okay, let's look at this one now. Which of these equations is valid for the circuit below? You will have a question like this. You have one. We had one in the notes and all the old tests. So, looking at these, which of these is correct? Which of these equations? All right, let's stop at 1:10. 5 more seconds. Just guess if you're not sure. 1:10. And look at this. C is right. So you will have one of these. Hopefully everybody get that right on the test. But on these, you want to go through and look at each equation, and I lay them out in order, so you'll see, the loop that I'm applying the loop rule to. So here we have 2 minus I1. That's okay so far. I'm going with the current at positive 2 because I'm going from big to little. Minus I1 because I'm going with the current. And then at minus 2I2, and that would be correct, but I'm missing this 4-volt battery. So to make this one correct, I should have a minus 4. This one is 2 minus 2I1. That doesn't work because this is a 1 ohm, not a 2 ohm. Notice that our current, I1, flows only in this part of the circuit. I2 is here, I3 is here. 2 minus I1, 2 minus 1I1, minus 4. That's correct. Usually batteries have positive potential change in potential, but when you go from big to little, it's negative. Minus 4, minus 2I2. So C is the right answer. I3 minus 4, I'm not going to go through the others, but C is the right answer. So you'll do a similar exercise where you go through. And then also for that same circuit, I'll have you calculate one of the currents in the circuit. Okay? I think you have 4 or 5 questions that are related to multi-loop circuits where you do the equations, you calculate the current in one. I have 1 or 2 questions about the junction rule, sort of looking at the junction rule, and then that might be it, I forget. But you'll see some questions about multi-loop circuits for sure. All right? Why did the coach go to the bank? He wanted to get his quarter back. These are online, so you can download them if you like and look at them. Let's go through, just summarize what we're going to see on the test, and then if y'all have questions, we can certainly look at those. So in Chapter 2, I like to call this Chapter 2B, because, we're just picking up with the capacitor portion of this chapter. You'll need to know basic stuff about capacitors. You need to know how to calculate the charge on a capacitor, and then also be able to calculate the capacitance given its dimensions. C equals kappa epsilon naught A over D. And I'll ask you some questions about, well, if I change one of these parameters of my capacitor, what happens to the capacitance, or what happens to the charge stored on the capacitor. We had some questions in the concept test that were similar, and you'll likewise see some questions like that on the test come Monday. You need to know the purpose of capacitors. They store energy. They're 2 parallel metal plates, sort of basic stuff about capacitors. Then you also need to know circuits. You'll see them in series, in parallel, and you'll see some combination circuits. So you'll see, I think, all three of those. A lot of circuits on this. You'll see you'll have to find the equivalent capacitance, and you'll need to be able to find the charge and the voltage or the energy on any single capacitor in a circuit. The capacitor circuits aren't, well, some of them are more complicated. Like some of them will have as many as, I don't know, say 5 capacitors in various combinations of series and parallel, and some of them will just have 2 or 3 capacitors. So some of them you'll be able to do real quickly, and then some of them you have to spend more time on. All right, so circuits. That's it. Chapter 3. We can come back to this and work through some circuits if you want, because I expect that's sort of where you're lacking the most. In Chapter 3, you need to know current. You know, I is Q over T. I think I even asked a question like from OpenStax, and you had some in your homework too, about how many electrons travel through this, that sort of thing. So be able to calculate the current, be able to calculate the charge in a given amount of time, and then know what that means in terms of charges. We also had Ohm's law here. V is equal to IR. So for a given voltage, how does that affect the current? And you also need to know the definition of resistance R equal rho L over A. Similar to what we had with the capacitors, you'll need to know if I change something about the resistor, the length or the area, the cross-sectional area, then how does that affect the resistance? Similar questions like we had with the capacitors, we'll have those here. If I change the length, if I change the area. Look back at those concept tests and at the old tests and you'll see, although we've seen some of those questions in class as well. You need to know ammeters and voltmeters. What kind of resistance do they have? What kind of potential do they get across them? And then also how you hook them up. These are in your notes, so let me just summarize. These have a small resistance. Because they have a small resistance, they always have a small potential across them, a small voltage, and you hook them up in series. Small resistance, small voltage, hook them up in series. For voltmeters, they have a big resistance, like 10,000 or more ohms. Because they have a big resistance, they have a small current, right? Because big resistance resists the flow of electricity a lot, so you get a small current, and then you hook them up in parallel. So you need to know those 3 facts about each one and be able to pick them out. You do have a question. I think there's just one question about ammeters and voltmeters. There's no ohmic versus non-ohmic stuff. I mean, ohmic device follows Ohm's law. Power. You will see some power questions. Be able to calculate the power, resistance, voltage, or current of a device given the power or whatever properties you need to find that. We did questions like that in class or some in your homework. Look back at the concept test too. So be able to understand power and what that means and be able to calculate various things regarding electrical devices. Like I'll give you the power and I give you, say, the voltage and I ask for what's the current or what's the resistance, that sort of thing. That's it for that chapter. Chapter 4 is sort of the big chapter. Chapter 2b was sort of big too. But chapter 4, we deal with EMF, the concept of internal resistance, resistors in series and parallel, you have a couple of questions about each of those. I might give you a circuit that's just parallel or just series, or I might ask you questions like about the rules that govern those circuits. Could ask you to calculate something, the voltage or the current on one of those resistors. You'll also see resistors in combo circuits, so resistors in combination. That means that you have some that are in series and some that are in parallel, but all in the same circuit. We've worked a bunch of those, but you need to work a bunch more. And we can work these circuits in class, and you might be looking at it like, oh yeah, I know how to do that. But really, you don't know if you know it until you sit down to a blank sheet of paper. And when you do that, it really comes out. Do I really know how to do this? And so just keep working those things until Yes, I have mastered this. The test will be different from all the old tests and the questions that we worked in class, although I did pull some questions straight from OpenStax, so you'll recognize a couple of those. But they'll be different, but they'll be very similar to those tests. So if you can do well on those tests, then you can do well on this. But of course, you know, testing is different. It's a different time when you sit in a classroom and you just sort of have to pour what you know onto a paper. So practice, 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 I think. And get good sleep on Sunday night. Okay? You'll also see multi-loop circuits, a loop rule, junction rule. I have some questions that are devoted just to those rules, kind of like the ones that we've seen here on the concept test. And then multi-loop circuits. For the multi-loop circuits, you'll have to pick out the right equation. I'll give you a set of equations for a given circuit. You have to pick out the right equation. And then I'll also ask you to calculate the current, just one of the currents, calculate the current in one of the branches. Now, it will be, if you see the right loops to follow, then you'll see that it's not that difficult to calculate that current. But you have to be able to pick out the right loop. Remember, because if you write your equations, if I have a loop that doesn't have a resistor in it, that means the equation for that loop is only going to have one current, for which you can solve it fairly easily. In your homework, you have one where you have to solve a whole system of equations. That might be useful for you to go through. It allows stop at the point where the algebra sort of starts. Just look at how we write the equations. On the test, you're not going to have to solve a system of equations as you do in the homework. Is that clear? All right. And I think that is it for all the topics. No RC circuits, no household circuits. That was the end of Chapter 4. We'll pick that up. It's an interesting topic, but we'll pick it up after this exam. All right. What is, I don't know, what ails you? What's bothering you? The what? The multi-loop circuits. Yeah, let's take a look at that first. Let's see. Well, we have, let's see if I don't think we've done the questions in the back of your workbook on multi-loop circuits. So why don't we look at those first since you have them in front of you. You'll see some questions like this. It's not identical to this, but you need to know the rules for resistors in parallel and series. I think this is exam 2. Number 22. Okay, yeah, so your test will look very similar to this, where you'll have to find the right equation, you'll have to find a current, so here it says, consider this circuit, which of these equations is correct? So I want to start with my first equation. I know y'all can't see this, but you have it in front of you, I think, all of you? All right, so I have 3 minus 2i1. I start up at 3. I know I'm supposed to be going in this direction because it's positive 3. My electrons actually gain energy when they go from low potential to high potential. So that's going to be a positive gain of energy. As I go through the circuit, I get minus 2i1. So going through here, 3 minus 2i1. And then I come down here to plus 6. That's as it should be because my electrons gain energy as they go from low to high potential. And then it does minus 6i2. Okay, that's not correct. Oh, wait, no. It's not correct, actually, because what I've done there is I've come up here and then I've gone here. And so my loop started up here. Really, to be correct, I should come back to the original point. The loop rule applies to closed loops. You can't just do any loop. You have to start back at the same point where you started. Or you have to finish at the same point where you started. So A is not the right answer. For this next one, 3 plus 2i1, it's wrong because that should be negative 2i1 because I'm going with the current. It might have other problems too, but I'll skip it. I1 plus I2 plus I3 equals 0. here, I1 and I2 are coming into the junction. I3 is going out of the junction. So, so it should say I1 plus I2 plus I3 equals, excuse me, I1 plus I2 equals I3. Incoming currents equal outgoing currents. Well, on the junction rule, let me just take a little step aside. Because I give you a circuit on the test that has all sorts of different loops in it. It's not just a simple two-loop circuit like this, but it has several junctions in there. And I'm just asking you, you're not calculating anything or even writing a loop rule for anything. You're just showing me which equation is correct for the junction rule. So for those, you just take, don't forget about the rest of the circuit. Just take a particular junction and say what currents are going in, what currents are going out, and set those equal to one another, just like we did here. And so that must leave D, 5 plus 6I2. 5, it's positive 6I2 because I'm going against the current. So remember, with resistors, you have two directions that are relevant. You have the direction of the current and the direction that you're traveling in the circuit. If you're going against the current, your resistor sort of does what it's not supposed to do, that I have a rise in potential. And so here I have 5 plus 6I2, and then I come back down here and I get minus 6 because I'm going from high to low. It's like going down the slide, right? Minus to what? Minus to 10, right. I love that. I want to use that for the rest of my life to describe this thing. All right, so that's, I get a negative drop in potential. So D is the right answer. You'll have a question that'll be very similar to that. Different numbers, different circuit, but a two-loop, multi-loop circuit like that. And you'll have to pick out the right equation. You'll also have a question like number 23. What is the direction and magnitude of I2? So when you get this question, it's important that you pick the right loop. Because I could here take I2 and write an equation for the top loop. And it would have, you know, minus 6I2 minus 5 plus 2I1 minus 3, and then solve that in some way for I2. But notice that it also has I1 in it, so I have two unknowns. So the algebra becomes burdensome. But if you notice here, I can look at my lower loop in this case, because there are no resistors here, I can just write the loop rule for the lower loop, and then there's only one unknown. You will have to do this. So be prepared. I'm going to write it for the lower loop. I'll start going in this direction, so I get 5 plus 6I2 minus 6 equals 0. And then you solve that for I2. If it comes out to be negative, let's see, does it come out to be negative? No, I don't think so. I2 is 1 over 6. It comes out positive. That means that the direction for I2 is correct. Doesn't have to be correct. If it came out negative, that means that I2 would not be to the left, but it would be to the right. So here is 1/6 amp to the left, which is the direction that was labeled on the graph, on the diagram. Alright? If it was negative, if this value came out negative, the answer would be 1/6 amp to the right. Just a second, William. Well, you can't have a clockwise current here. It's either to the left or the right. Because that current only flows in this part. In fact, don't worry about clockwise, counterclockwise. On the test, I just say left or right. So like this would be to the right, this would be to the left. I know that you can define it in clockwise, counterclockwise. Unless it comes up negative. Right, now on your test, I assign some directions for you. But remember, the direction doesn't matter. You can choose whatever direction you want. Alan?
So if you came out I'm just trying to figure out how you can tell when the direction is.
I understand. Yeah, so if it comes out negative, she's asking about the junction rule. If it comes out negative, does that affect the way that you write the junction? That's what you're asking, I think. No. So you don't know if it's right or wrong until the end, the direction. you write your junction rule as you've labeled the currents. And then at the end, if you find that one of the currents is negative, then you just put in that current to the junction rule as a negative value. But it doesn't affect how you write the junction rule. The junction rule is only affected by the directions that you draw the currents. All right, that's a good question. Sometimes students get confused with that, but the negative doesn't really come into play until the end. As you're writing your equations, you keep them based on how you label the currents. Joy? Oh, so why did I add this? Because I have, yes, why do I add the 6-volt battery here if the current's only flowing here? This battery is affecting the current here. It affects the current here. It also affects it up here. And so I have to include it because I'm looking at this loop. Let me back up a little bit. When we write the loop rule, we write the loop rule for a closed loop. And so if I just write the loop rule from here to here, that's not a closed loop. That's just, a branch in a circuit. And it doesn't apply. I have to start here and then go around and come back to the same point where I started. Well, let's see, in this case, I started here and come back to the same point that I started. I could do it for any loop. I could do it up here too, but algebraically, it's easier to solve for the bottom loop. Did that answer your question? All right. Something else on multi-loops? There are 4-ish questions, I think, maybe 5. I think 4. If you see anything like this, that's all RC circuits, so none of that stuff is on there. Huh? Sure. This is similar to the one that we had in the concept test. I think we did it in class 1 similar. Which of these resistors has the smallest current? On these, don't worry about do worry about the numbers, but don't worry about calculating anything. You want to look at the current as it flows through here. As it comes here, all of the current goes to this resistor. So if I ask which resistor gets the most current, it's this one, because it gets all the current. But then when it comes here, it splits up into 3 pieces. It splits into a piece here, and a piece here. Now electricity will flow to the least resistant spot. So I have 4 ohms, I have 6 ohms here, not 2, not 4, but I have 6 ohms, because I combine these 2 resistors, 4, 6, and 1. So the one that will get the most current is the one that is the least resistant to the flow of electricity, and that's this 1 ohm resistor. So that's R5, D is the right answer for that one. Oh yes, I'm sorry, you're right. What did I say? It's either R3 or R4, so that would be C. Okay. You should also be able to take this circuit and calculate the real current by the equivalent resistance. R1 right here, I'm looking for the one that has the smallest current. R1 actually, whatever current is coming off of this battery goes through R1. So this one actually gets the biggest current. All right. Right, 4 wasn't a choice. So either 3 and 4, they have the same current. I could also say R3 and R4. It has the smallest current because this has the biggest resistance. I'm pretty sure you had a similar question on that. Asked me to sort of think about the currents and how they're distributed. But as I said, you should be able to find the equivalent resistance of this, as well as the current or the voltage on any one of those resistors. I think there is a similar problem for that. Let's see. 13, yeah. You know, the hard part about 13 is just realizing what this circuit looks like. Because it's sort of written in this funky way, and you need to realize, how can I write this in a way that we're more familiar with? And so the way you do this I always come off the big side of the battery, just because it doesn't really matter if you come off the big side of the battery, but it just makes me feel better. Because I come to a circuit I don't understand, I say, okay, I'm going to start with the high potential side of the battery, the positive side of the battery, and I go in this direction. So I'm going to redraw it, and my 10 ohm resistor, and then I get a junction right here. And that junction tells me that I got a parallel branch. And on one parallel branch, I have two 2 ohm resistors. And then on the other branch, I have one 4 ohm resistor. And then they come back together, right here. And they go back to the battery. So I have 10 ohms, 2, 2, and 4 ohms. And I think when we see this circuit, it begins to make a little more sense. I hope so. If not, that's okay, but we need to practice so that this one looks better. So now I go through the process of figuring out the equivalent resistance. What am I looking for? The current through the 4 ohm resistor? That's right. The equivalent of these two is 4. A 4 and a 4 in parallel, that's 2. That's 1 over a quarter plus a quarter is 2. So I have a 2 ohm resistor here and a 10 ohm resistor here. So my equivalent is 10 plus 2 is 12. I have 12 volts. 12 volts through a 12 ohm resistor is 1 amp. So I have 1 amp here, which is 10 volts. That gives me 10 volts. That means that across here, if I have 10 volts across here, I have 2 volts across this whole thing right here. So that means this resistor has a voltage of 2 volts. What does this resistor have? What voltage? Second thing. What is the 2 ohm right here? What does it have? What? It has 1. All right, let me write this down just a second. We'll get to your question. So I have 12 volts here. I have 10 volts. I have 2 volts. I have 1 volt and 1 volt. Let me sort of recap what I said. My equivalent is 12 ohms. With 12 volts, that gives me 1 amp of current. If I have 1 amp here times 10 ohms equals 10 volts. And up here, 12 volts minus 10 volts, that's this minus this, is equal to 2 volts. And so I have 2 volts across both branches of this parallel branch, 2 volts here, and 2 volts here. But resistors in series split up voltages, so I have 1 volt and 1 volt. Only because they're identical, they share that they have the same voltage. They split it up evenly. Clear? Okay. A couple questions like that on the test. 2 or 3. The answer for this question is 2. Oh, it's asking for the current or the voltage? Oh, it's asking for the current? Yes, so I have 2 volts, 4 ohms, I is V over R, 2 over 4 is 0.5 amps. 3.5 amps. Yeah, anytime you get any two quantities, remember you can calculate the third. The same is true for capacitors. Because V equals IR, Q equals CV. If you know any two of the quantities, you can find the third.
What does you of all of the numbers before having the fractions when you do that, like 0.9 and 0.7?
Most of them work out evenly as integers. There are a couple that work out as decimal numbers, so I try to limit the calculator use as much as possible, but there are a couple that you need it. And then of course, like calculating the area like for the capacitor, you'll need your calculator. William? One day, no calculators. Every year I say I'm going to do it. Not for you. But what would you think about that? Like if you, but no, like you say it's awful because we use a calculator all semester. But what if you came in the fall and you're all bright-eyed and bushy-tailed, and then I came before you never met me and I said, no calculators on your exams. And you would just say, oh, well, that's just the way it is.
I would not. I would not.
Huh?
You would not be motivated.
But on the MCAT, which many of you are going to take, cannot use a calculator. Y'all knew that, right? And some of their problems are difficult. You have to know your cosines and your sines and tangents and all that business. So that's why, just to help you pre-med students. Okay. As I said, any household stuff you're not going to have. Know how to calculate your resistance. Listen, you will have a question like number 11. So let's just go ahead and work through number 11 because I don't want you to freak out. Let's just sort of take some time to work through this. Because it's a little bit different than what we've done, but it's a good question. It'll be similar to this, where I tell you the voltage on one of the resistors and then ask you what is the voltage on the battery, which is sort of opposite of what we usually do. So we need to find first the equivalent resistance. I have 6, 3, and 2. 1 over 1 over 6 plus 1 over 3 plus 1 over 2. Common denominator is what? 6. So this is 2 over 6, 3 over 6. That's equal to 1. That's 1 ohm and 4 ohms. And I know that I have 8 volts here. A couple ways you could approach this. You could think about how the voltages are distributed. If I have 8 volts across here, it has to be 4 times the voltage that I have here. So that means I have 2 volts here.
What about the 2 ohms, like R4? You did the equivalence of
Did I do this wrong?
right.
Yeah, I just sort of, sorry, I was just thinking on the paper. So I have 6 ohm, 1 over 6. These two are together 3 ohms, 1 over 3, and then I have 1 over 2. And so that goes to 1 6 plus 2 6 plus 3 6. 1 plus 2 plus 3 is 6, so that's equal to 1. Yeah, that's right. All right, so back to what I was saying. So if I have 8 volts here, then I have to have a smaller voltage by a factor of 2. I have to have 2 volts here. But if you don't want to think about it that way, you can say, well, 8 volts and 4 ohms, that's 2 amps. 8 over 4 is 2. So I have 2 amps here. That means I also have 2 amps here. So that means I have I times R, 2 times 1, I have 2 volts there. If I have 8 volts and 2 volts, that means I have 10 volts here. All right? So you will have a question similar to that.
What is that
For capacitors. Yeah, so be careful with your capacitors and your resistors. They're very, very similar. Right? Capacitors and resistors both split up voltages when they're in series. They both have the same voltage when they're in parallel. But capacitors, their equivalent is a little bit different. It's flip-flopped. If you forget, it's on the equation sheet, but, you know, who wants to look at the equation sheet, right? And otherwise, I think that's it. Yeah, but just, we wrote down all the rules for capacitors and resistors. I'd go over that. I have a question, at least one question about those rules anyway, so you need to know them. You need to know them to work the circuits. All right. Any other things stand out here? You know about EMF and internal resistance, about your voltmeters and ammeters, your resistivity. Sure. Okay, so I have 2 light bulbs. One's a 100 watt and one's a 25 watt. Now, what is it? Which one has the greater current flowing through it? E is equal to VI. We have three equations for power. I've chosen this one because I have a constant voltage. When I have a household, everything operates at the same voltage. And it says that here. That my two light bulbs, they both operate at 120 volts. And if I have constant voltage, the one with the bigger power has the bigger current. And so I'm asking for the one with the greater current is going to be the 100 watt. Because a bigger power means a greater current. But you know what? Think about it in this way. And this works for resistance too. If I have a greater power, that means it's a brighter bulb, right? 100 watt is brighter than a 25 watt. That means that I have more electrons traveling through there that give more energy. And so if I have more electrons traveling through, then I have a bigger current. Or you can think about it in terms of resistance. That if I have more electrons flowing through, the 100 watt, that means that it must have a lower resistance because it's allowing those more electrons to flow through. And that comes out not here, but E is equal to V squared over R. Notice my V is constant. If I have more power, I have a lower resistance, or vice versa. If my resistance is smaller, I have a bigger power. It's like in your hair dryer, when you look down the tube of your hair dryer, all that is a wire. It's just the heating coil is really just a wire. It's a wire that won't melt when it gets hot. It has a very small resistance, and that's why it puts out a lot of power. It also carries a big, big, big current. Okay? Look in the concept test. We had a couple different questions, variations of that. But I'm pretty sure you see questions like that on the test. So a lot of questions will look familiar, but they'll be different too. Let's see, what other topics do we have? Anything else standing out to y'all? I think number 19 on that old test. Yeah, no RC circuits. Yeah, so be careful. If you see anything that says RC on the old test or anything that looks like this, it's not going to be on the test. They might be sort of interspersed a little bit because usually I cover all of chapter 4, but you know, the way our dates fell, it just didn't work out this time. No, that's a household circuits. I'm sorry for that. There's no easy way for me to go through, and if you have a question over the weekend, we'll be back Saturday evening. Just shoot me an email with it. Any kind of question you have, and I'll address it. I think I mentioned this, but we'll see some OpenStax questions from your tutor assignments from those first 5 or 6 questions, not the last 2. So some of those I just pulled verbatim. Most of them that I pulled, I think there were 5-ish, maybe 6-ish that I pulled. I pulled them, I changed the numbers, you know, but they're still the same questions. So I would go back over those and just look at the questions for review. Yeah. Okay, so an internal resistance. What this is I have a battery that has an internal resistance. So we think of our battery as having an ideal source of electromotive force, and then it also has this internal resistance. That's why your batteries get warm when they provide a current, because they have this internal resistance. It's not an actual resistor, it's just sort of, you know, the device itself has resistance. And so it says that the potential across this is 10 volts. And I want to know what is the EMF equal to. Well, 10 volts, that's my change in potential, is equal to the EMF minus the current times the internal resistance. That equation is on your equation sheet, but it's really an application of the loop rule. And so I say 10 volts is equal to the EMF minus the current, which is 2 amps, and 1 ohm. And so my EMF then is equal to 12 volts. In an ideal world with no internal resistance, this would be 12 volts. But because I have this internal resistance, I get less off. I know you guys don't have ammeters in your vehicles anymore, but used to we had ammeters in our vehicles. If you have an older vehicle, you might have that. And if you ever notice on those, when you turn on your air conditioner, the current in your system drops. And the reason is because, or excuse me, not the current, the voltage drops if you have a voltmeter in your car. The reason is because you're increasing this current, and that decreases the change in potential, your voltage, your actual effective voltage. All right? But y'all don't have, anybody have a voltmeter in their car anymore? Like an actual dial on your car is like later than the 80s or whatever. You don't have that. Okie dokie. So about the OpenStax, I haven't written it up for the syllabus yet, but the way it's going to work is there will be your OpenStax assignments will count for 20 points of extra credit. That's not insignificant. I mean, it's 20 points. It just sort of goes into the pool. And in order to get that, it's really sort of an all or nothing thing. You have to get, say, 60% threshold on your OpenStax. You know, there'll be some wiggle room. If you're at 55, then I'm not that big a deal about it. But, you know, use the OpenStax as a good place to practice, because it is a good place to practice for the exams, because your questions will be similar. And sometimes I'll just pull questions outright from those questions. Alrighty? Y'all have a great weekend. If you have questions just for me, please come see me, because I won't be around this afternoon.